Saxon Algebra 1/2. We're continuing on with lesson 117. Sorry to interrupt. Okay, so this is what the Pythagorean is really good for. If we have a right triangle and we have two sides but not the third, we can easily figure it out using the Pythagorean Theorem. So I look at this and I have to orient myself to make sure I know which are the legs and which are the hypotenuse. This is the right angle, so this is a leg and this is a leg. John already told me to call this one A. Okay, so I'll call this one B. And then the hypotenuse is always the C. It has to be that way in the formula. Okay, so now I'm going to just recreate like this. I'm going to say A squared plus 4 squared equals 5 squared. We really never have negative numbers in using the Pythagorean theorem because it's geometry. There's no way any of these sides could be a negative measure long. So there's no negative, so we don't really have to worry about buckets in this, although you could easily put buckets in there. All right, let's do the math. A squared plus 16 equals 25. We subtract 16 because we want to isolate the A squared. A squared equals 9. Now this ties in to what we were doing just a few minutes ago, right? If something squared equals that, then you have to consider the plus and the minus. So we have to say A equals plus or minus 3, but is there any way that this length could be a negative 3 units long? No. So we can just say A equals positive 3, and that's our answer. In geometry, we can disregard negative solutions if they don't make sense in our picture. And that is one thing I think is super cool about geometry. I like that very, very much. Okay, let's do another one. And that's why I wrote the 3 in there, is because I have memorized, and you will later, that a triangle that has a hypotenuse of 5 will always have legs of 3 and 4. That's not true. It could have different legs, but rarely. The whole numbers work out that way. That's a pattern, a 3, 4, 5 triangle. We'll talk more about that later. But that's why I wrote the 3 there, because in my brain I knew that was going to come out to be 3. Okay, here's another one. Now I want to draw the triangle the way John does, because it's floaty. And at first that's really upsetting and kind of hard to draw. But here's the thing, as long as we know where the right angle is, as long as we see it, we know Pythagorean will work. And as long as we know which sides come out of it, then we know which are the legs and which is the hypotenuse. So we're fine. Here we go. It's 4, it's 5, and it's M. Okay? Now, we might get excited and go, oh, I said that 3, 4, and 5 always went together. And we think, oh, well, look, here's another one. Except this time, the 4 and the 5 are the legs. Here, 5 was the hypotenuse. So it's not going to be the same. This one's different. All right, so let's see. Let's get oriented. Which one should be A and B? Like this. I like to label it so that I'm sure what's what. And then this M is going to go in the position of the C. It's okay if I use the M squared, just like I'm going to use the 4 and the 5. But I just want to know which, I use A, B, and C just to help me know which position they go in. So now I'll write it out. 4 squared plus 5 squared equals M squared. 16 plus 25 equals M squared. 41, excuse me, 41 equals M squared. Aha! I take the square root of both sides and I'm going to flip it around. M equals positive or negative square root of 41. 41 is not a perfect square. It's not going to come out even, so we can just leave it in that form. We get to disregard the negative root, so we can say M equals square root of 41. That's our final answer. See, it's kind of satisfying to just leave it in that form and be like, I don't know. If I had a calculator, I could figure it out, but otherwise, we can't calculate those roots like that. Our brain, we don't have a process for doing that. Okay, the last section of this lesson, I want to tell you what it is, and I'm going to tell you why we're not going to talk about it. It is a demonstration of the Pythagorean theorem. It's John proving to us why a squared plus b squared equals c squared. And here's the thing. all this. I just want you to see it. I don't want you to pay attention to it. Here is the way I believe math should be taught. First, you learn how to do the operation. Forget the why, just tell me the how, right? And then once you really get the hang of the how and you know how to grind the numbers through, then it's a little more interesting and we all have a little bit more bandwidth in our brains to talk about the why, to talk about the philosophy and the reasoning behind it. That's not interesting to you right now. I know that very well. You're just like, what? Which ones are the A and the B and the C? What's that all about? I'm not going to give you some big, long, fancy story about why it is the way it is. We're going to get to that later, but not this year. So we're going to stop short of that. I want you to just have the practical details here on the Pythagorean theorem. The legs are the ones that come out of the right angle. They're the A and the B. The hypotenuse, where the Captain Kangaroo cuts with his scissors, that's the C. That one goes on the other side. These get added together. That's why it doesn't matter which is A and which is B, because you add them together, and in adding, oh my gosh, I wrote it wrong, you guys. I wrote it wrong. Please correct it. I did it properly, but I forgot to put the squared down when I wrote it. It's squared, squared, squared. It should be like that. Oh my gosh, I'm so sorry. I hope that didn't make you crazy. That's the Pythagorean theorem. Okay, now I'm done. Thank you, goodbye.